And we are live. So hello everybody once again. My name is Sanket and I welcome you all into today's session where we will go ahead and talk about a very hot topic, data science versus data engineering. Can you really separate them? Well, career in the field of data science in the recent years have seen soaring demand with a growth rate of around 27% in the last 2 years. As companies continue to focus on generating, collecting, and analyzing big data to help them run their businesses, the demand shows no sign of slowing down. Today's webinar is to give you insight into the key difference between two of the most prominent professions within the information realm, that is, data scientist and data engineer. And today's session will cover everything that you need to know to make an informed decision about the career that best suits you. In order to go ahead and talk more about it, I have with me today Darren Lefko, who comes with more than 20 years of experience. Just a small brief about him before we go ahead and get started. Darren Lefko is CEO, Lem Solutions Limited. Darren obtained his master's degree in physics from Imperial College of Science, Technology and Medicine, London, and started his career as a satellite engineer. Following satellite engineering, Darren has since then been involved into credit market and has created emerging market and developed markets in both investment grade and non-investment grade bonds. Darren has abilities across asset classes, including debt, equity, derivatives, and others, where the criteria to maximize risk-adjusted return enhancement of profit. Darren is proficient in Python, Visual Basic, JavaScript, Node.js, C++, Fortran, and has been involved with machine learning, artificial intelligence, and big data for the purpose of trading and decision making, which he has huge passion for when it comes to solving business leads. He also falls under the top 1% of Stack Overflow, so he is probably as good as it gets. So without further ado, let me go ahead and pass on the mic to Darren so that he can go ahead and get this session kickstarted. Darren, the stage is all yours.
Can you all hear me?
Loud and clear.
Right.
But we can't see you though.
Okay, the host has stopped my video, so I think do you restart the video or do I? I'm blocked from opening it.
Can you try it again? Should be good now.
Bear with me. Start video. Okay, I think I'm there.
Yes, you are. It's all yours.
Okay. Can you see the screen behind the screen as well? Presentation?
So I can see the PPT, if that's what you mean. Yeah.
Okay. So if I page forwards and page backwards, you can see that.
That is correct.
Good. Okay, perfect then. In that case, I shall start. I guess before I even begin, I was shown, I think, 4 or 5, well, about a dozen topics, and I was asked, can you pick a few? And this one kind of like stood out as one of them. I never even thought that this was really a question until a question was posed, but I didn't really think of a difference between a data science and data engineering. So I was like, oh, fantastic! That looks like an interesting topic to discuss, really. So we'll go from there. In particular, it's data science versus data engineering, and can we really separate them? And again, I probably go through this a tiny bit quicker, but I've already been introduced, so thank you very much for introducing me. You've done a great job, probably a better job than I do of introducing myself. But yeah, I have done a master's degree in physics. That was at Imperial College before 2000, so significantly longer than maybe some of you have even lived. And I started, having done physics, I started doing satellite engineering. So I was an engineer, And then I moved into quantitative finance for the purpose of trading. So quite a large part, effectively, of a data scientist. So the question is quite pertinent because I've been both of those roles, and without even knowing it, effectively. Just some of my contact details and who I am, just in case you do or don't care. My LinkedIn, I've got a reasonably enough unique name that you could always pull me up if you wanted to. And there's an email address and a Twitter, just for the sake of it as well. And a link also to, again, my LinkedIn profile, and I guess a link to this Zoom, but I presume that you guys will all be distributed this anyway. So I'll leave that down to the course organizers. But I believe this is being recorded and everyone can watch it back if they want to. And finally, on the introductory bits, a couple of things that I've done recently, at least. One is writing a book on Python programming, which actually got me involved in all of this aspect. It's not something that I'd done before. I've always been in industry, but I just felt kind of like the knowledge was enough there that I could contribute in this space as well. And there's also a quite well recommended book on trading and the life cycle of a quantitative trader. Again, it's something that may or may not interest you if you're on the bias of the finance part of the quantitative and data science type of space. But as we'll see anyway, going through the presentation, that it's actually quite a way larger than this, and you know, the finance sector is one of maybe 10 sectors you know, that we can discuss and go through. So I'll move on, which is I guess part of the preamble, or at least what I had on the initial email that was kind of like there. And it's basically, are you interested in the booming field of data sciences? Are you confused by which career option to pursue, data science or data engineering? Or maybe simply you want to understand the difference between these two vast fields. They're not my words, they're the words of the course organizers, but in a way, very applicable. So I thought I'll put it there anyway, just so that you have it. And likewise, with regards to aspirations, most aspirants in the data science field want to land the coveted role of data scientist. It seems to be a big thing. But did you know that the tech giants such as Netflix, Facebook, Amazon, etc., and I can give you a whole host more of those, are hiring data engineers like never before to process massive amounts of data that they're gathering, and that's pretty much true. And finally, this webinar is a great opportunity for you to hear from eminent industry experts. Hopefully I'm classified, at least in part, as some kind of industry expert. At least inadvertently, I've been in the industry for a long time, not having known that effectively I have fulfilled both of these roles in abundance. Yeah, and you get a chance to see data science and data engineering industries up close. So today's presentation, I've been given 2 hours. I know that the previous presentation I kind of like slightly ran over, so I'll try and stick to about 90 minutes of talking and 30 minutes maybe, or 15 minutes of question time, because some of the time's gone beforehand. And there's about 60 slides that you guys will get to see. So hopefully 1 to 2 minutes per slide. So I won't like you will be entertained enough, and the slide frequency will rotate fast enough that you know that you get a full broad appreciation within the time that we've got, and also you will have time to ask questions at the end as well. So really moving on, and this is, I guess, the beginning of the talk. Everything else before this was pretty much, we'll call it the preamble and the introductions. And the first thing really to be said is the obvious question, can you really separate them? And in order to answer that question, let's ask, I guess, the first two most obvious questions in that scene. And it's, what is data science? And also, what is data engineering? So if we can answer those questions, we can at least in part embark upon our way of answering, you know, the separation between the two. So, by the way, there's only going to be 2 or 3 slides that have this much writing on them. So don't worry, they're not all going to be blazoned with tons of stuff. In fact, there's probably more writing on this slide than the next 50 behind it. But I just thought I will put on effectively like the understood or colloquial definitions of data science, and also afterwards data engineering. And then I'll just pull out some of the keywords afterwards. But just in summary, data science is a field that uses scientific methods and processes and algorithms and systems to extract knowledge and insights from structured and unstructured data. And we'll discuss a tiny bit about that later on. It is a multidisciplinary field that combines domain expertise, programming skills, and knowledge of maths and stats, as well as other mathematical type of things, to understand and analyze data. Data scientists apply machine learning techniques, but amongst other techniques, I should add, to build predictive models. They mine large data sets, and we're looking all the time in this space for patterns and trends, and communicate their findings to stakeholders. The plain English version of that is we're telling people a story about patterns and trends that we've discovered, things that just happen to be common. It always rains on a Friday, for example. It doesn't, but just things like that. Some common applications of data science include building recommendation engines, fraud detection systems, and prediction systems for the financial markets. Now that's a lot to get in. I don't expect you to kind of like in any way to like take this bundle of one paragraph of data that's kind of like there, but I've just put that there, and we'll pull out some of the keywords. And likewise, when we go on to ask the same question about data engineering, it actually even had more than the data science stuff to write. So I kind of like condensed it down to a paragraph. But what is data engineering? Data engineering is the design, construction, and maintenance of systems that process and store data for the purpose of analysis. It involves tasks such as extracting data from various sources, cleaning and transforming the data, and setting up pipelines to automate the flow of data. Data engineers may also be responsible for securing and protecting sensitive data. The final part of it, and I've kind of like highlighted this bit in orange, is they often work with data scientists to help them access data for machine learning models. So there's a lot of keywords in both of the data science and data engineering parts, and I've kind of like highlighted them in yellow. And I'll be putting them up in the next couple of slides. We're looking, for example, here in the data engineering part, we're looking at like design, construction, maintenance, extracting data, setting up pipelines, and so forth. And if I just hover back one page, again, in the data science part, we've got scientific methods, extract knowledge, programming skills, mathematics, machine learning, patterns and trends. So kind of like the other part, you can glaze over the grayed out, like nearly consider the grayed out parts, just glaze over, and we'll focus on the keywords to get a core difference between the two. And I'm going to do this initially starting just by way of a word comparison. On the left-hand side, I pull out data science, and on the right-hand side, you have data engineering. And one of the, I guess, the most obvious thing that should stand out is both contain the word data. So we're talking about the same thing in some kind of way and operating on the same thing in some kind of way. But what we could say is that some kind of way is in two different ways. But critically, as part of this, the difference is the science and the engineering aspect of it, and not so much the data. The data is the central core part of what we're doing. And this difference should be clear. Or the question is, or is it? So we go on and take a look. But let's just do a side-by-side comparison. And again, like I put into two columns, data science on the left-hand side and data engineering on the right-hand side. But the bulk of these keywords, and I could have fitted more into the slide, but I kind of like want to keep it relatively simplistic. So I took just the first half dozen of each of the keywords in the previous paragraphs that we saw. And in an attempt to kind of like patch them together and make a side-by-side comparison, but it will draw some obvious differences or similarities between the two. So on the data science side, again, we see things like scientific methods and extracting knowledge. We see programming skills. Programming skills isn't necessarily restricted just purely to data science, you might argue, and that would be true. Nonetheless, it's fallen on that side. Then we've got something like maths and statistics, again, that falls on the data science side. But the reality is maths and probably maths and engineering that falls onto the applied maths that falls onto the right hand side, which is the data engineering side. So there is, so you could argue or challenge at least that the left hand side and the right hand side in parts also could flow to the other side. And then again, on the when we think about data science, one of the things that we do talk about a lot or consider is machine learning, and also actually artificial intelligence and all of the likes of this new genre of science that's effectively been born in the last decade, although it's existed before. We'll go into some of this, but the processing power has enabled machine learning, and machine learning falls into the data science aspect. It's kind of like one of the things that data scientists back in the day might have dreamed of having enough processing power to do, and now they're beginning to be able to get that. And finally, this probably does very much fall into data science, is patterns and trends. It's very much the scientific part of it is the attempt to find these patterns and trends. On the data engineering side, likewise, you've got design and construction, and that could be to do with databases, for example. It could also be to do with connectivity and the pipelines involved in all of that kind of stuff. And then we go on to extraction of data. That's very much a data engineering role as opposed to a data science role. And on that particular line, I've actually put them side by side, but they both have the word extract in there. You are extracting something in each case. On the data science side, you're extracting knowledge. On the data engineering side, you're extracting data for the purpose of generating that knowledge. And you know, how do we extract this data? Like, if, for example, like that data could be in the format of you're going to an election and you're counting all of the Labour or Conservative votes, you know, if you're in the UK, or, you know, if you're in the US, which might be a more global example, you're counting all of the Republicans, or, you know, the Reds and the Blues. Are we able to extract that data and pass that data into the system in the ways that we need to? And that's part of the automating of flows. Like, can we get that into the systems correctly? If we were to compare that with like other voting mechanisms, for example, if you go onto like popular TV shows now, you can sort of like do telephone and internet votes. One might argue that they're way more efficient in the mechanisms for getting that data into the system. So a typical television type of voting scenario can draw like 30, 40, 50 million votes within the space of an hour, whereas an election that's done on paper by people and so forth, it still passes itself into a system, but that process is much slower. It can take days to a few days to produce that same thing, because you've got humans running around. So an automation of flow in some kind of way. And that's just a very broad overview example. And then also there's the point of maintenance, and that does fall down to the data engineer. And kind of like, what is maintenance? Like keeping up the systems, the databases, make sure all of this stuff is running and operating properly. Then is the setting up of the pipelines. So that's making sure that the connectivity between the different interoperable systems, that some of which are required by the data scientists, that they're all operational and they do work. In its most simplistic case, you might even have something like a language that I've used like Python, and you want to integrate that with you know, a web language like JavaScript, and you in some way want to pull out the data, and you just need to make sure that the number of arguments going into a function is the correct number of arguments, that it works in a certain way. And then there's other more mechanical parts of that too. But nonetheless, all of that has to be working, otherwise the system just breaks at some point. And finally, protecting sensitive data, a hugely important part. There's two aspects to data. And the aspect from the data engineering part, at least, is making sure that the integrity and the security of like usernames and passwords and people's private data, when it comes to people type of data, is secure in that capacity. And I shall move on from there. But we have some keywords in data science. Some common keywords include machine learning, that's artificial intelligence, data analysis. So we could ask ourselves the question, what is data analysis? We've got data visualization as well. What is data visualization? So we do some sort of analysis. We do some kind of predictions as well. What are our predictions? We create these visualizations once we've done our analysis, which is mathematical or computational. We get a mathematical or computational result that comes out of this, and kind of like we as humans need to show this or display this to ourselves. That moves into a data visualization aspect. So it could be like matplotlib or Seaborn or something like that, a package, or it could just be a chart that's posted on the web that updates. And then once we've got the visualization part, we're also effectively looking for a prediction. Maybe what can our model tell us? Can we get some forward guidance? Can we do some data science, for example, on the weather? And are we able to harness and use this in some way, not only just drawing the nice weather charts that are around, but can we make a prediction based on what's going to happen in the future? You know, will a hurricane, where will it hit, or will it be a rainstorm? And again, some of these things, you know, we've lacked in the past in terms of our ability, our computational processing power. We haven't had these, and then as advances have been made, we've become better and better. So, you know, if you cast your mind back, well, we can't even, but if we like look back even up to 100 years or 200 years ago, the way that they looked at weather was completely different. They didn't have the tools or the technology or the processing power that we have. And part of this prediction comes from the modeling side of it. And then we've got data governance and security, and funnily enough, like, you know, we're going to see that manifests itself also in data engineering. But, you know, what do I mean by data governance and security for the purpose of data science? And it's more like looking at the side of the science part of it. So our behavioral patterns over the data, like how do we measure the data? If, for example, I'm going to measure an election and, you know, the votes in England between Conservative and Labour, and I kind of like want to get a prediction of like which one is going to win between the two parties, and I happen to stand outside a conservative rally and take votes from all of the people that are walking out of the rally, I'm going to get very skewed and very biased data. So I need to be careful about how I manage the data, and that's a data science aspect, as opposed to like the security of the data, or you know, making sure that we keep user records private. So it's how we use the data. And one classic, and probably, well, not classic really, a very recent example that we're all aware of is like COVID, like how we display that type of data. And if we were to look at it from a purely scientific perspective rather than other political aspects, we might kind of like just measure the population of the planet and say we're an 8 billion planet, and compare COVID to other pandemics and see the damage that they did. And we might, like, for example, we might compare it to I think the Black Death, or the what was known as the Spanish flu at the time, where the world population was just 1 or 2 billion, and the number of deaths in the first year was 50 million. If we compare that kind of data and look at that for COVID, we have 8 billion as a population, and the number of deaths in the first year was far less than 1 million. So you could argue, like on a scientific basis at least, that COVID wasn't a pandemic, at least in the scheme of what we might have considered to be a pandemic, by a couple of orders of magnitude. And again, it's how that data is portrayed. So some may say that's good or bad. There might be discussions about that kind of thing, but nonetheless, that's all a core part of the data governance part of the data science. And then we move into something that I'm going to say is a bit more interesting, but like certainly different, or much more forefront in our minds, which is things like natural language processing. That again falls into the machine learning category, but we're at the point now where we're beginning to replicate the human brain and how we think. And one of the nice things is kind of like, and chat GPT is a new thing that's popped up recently. But one of the things that's come out is how we interact with computers and how they can sort of like harness our ability in terms of natural language, just like how we can the mathematics around it and our understandability, and can we get it more like a neural network and less like a chatbot that we used to know of 10 years ago. And finally, in data science, well, maybe the last keyword, but there was many more. This list was much longer. Predictive analysis. Again, I think that should be intuitive. That all kind of like falls very much into data science. We want to ultimately, our goal is some kind of analytics that gives us some kind of predictability if we can. That's kind of like one of the ultimate chalices. So we move on to keywords in data engineering. And some of the common keywords in data engineering are data ingestion. So how are we going to get the data into the system in the first instance? You know, I previously in the previous slide, spoke about elections, like they're done on paper. You might have, for example, just even like by way of this, like the camera that's pointing at me right now, it's a CCD array. It's capturing data that very much has got no human component to it. So it's a different type of ingestion, and that data in some ways passed into a system. If we wanted, or if I was to, and actually one of the nice things I wrote in the book was how to kind of like, if you take like a pen, and if I was to wave it around on my finger or put a little color on it, you could get the screen to track that. So that's ingestion of that data, and how quickly or how well can the screen track that, and then it can sort of like draw a little line and follow a circle, and you can play a little game on your screen with like your hands with different color pens. So, but that's all part of the ingestion part. And if we were to look at like a completely different field as ingestion, for example, trading, the trading field, that's completely different again, because it's just trade data. So you get loads of transactions and you're passing them into a system. Quite often these might be like, mini JSON files or CSV files, and you might be passing them into some system. So that brings us on to data storage and management. How are we storing this data? Initially, you might be storing CSV files, XLS files. You might be moving on to bigger things like database and so forth. So database management systems. We've got all of that component. And then data processing and transformation. So once we've got this data, we've stored the data, like what do we do with it? Like, and how long does it take us? We've got a cost in terms of time and in terms of storage volume. So there's two costs to us. How much data that we can fit into our data warehouse, because we're limited on that aspect until we can build bigger and better things. And maybe even like, again, like a great example of that will be if you were to just to take your mobile phone as you've got now. And I literally, like on my mobile phone a few hours ago, I just decided to delete a whole host of pictures, and it was about 3,500 photos on the phone. And if you go back like 50 years ago when the space race was on, that was probably more information than all the information that was required to send man to the moon. And yet that just sat on a WhatsApp chat on my phone, and I deleted it like as if it was nothing there. But that would have been a huge amount of processing for power back in the day. So like we have those things, and this is one of the challenges of the data engineer. And likewise, data pipelines, and the pipelines refer to, well, they can refer to, for example, just the internet connection. So I want to retrieve data off of the internet. And if I want to retrieve a large amount, there's a latency on the internet, and I've got a bandwidth that's available to me, and I have to operate within that. Do I use a cabled system? When you have an office system or you want high frequency trading, do you put the servers inside of the office and then have wired connections? So they do all those types of aspects that need to be thought about. And that leads into like big data technologies as well, because when you look at the larger companies, all of those issues that I've just mentioned they just scale up. And if you look at the likes, for example, of Facebook or Google, their data warehouses and their big tech has to be absolutely humongous, just because of the petabytes of data that are collected pretty much on a daily basis. It's a humongous amount of information that these large companies have, and enable like the ability to handle that all of a sudden. It is not a simple thing. It's not a laptop process anymore. It's not a computer process, and it's no longer even a server that fits into a room. It's more like a small village of technology. And then we've got the data modeling part of it, but not so much the data modeling on the data science side, but really, again, the complexities of speeding up processes. So you might look at like infrastructures of like Matplotlib and NumPy and Pandas, and how they operate, and can we ilk out another microsecond of speed? And whilst that microsecond of speed didn't make a difference, on the small scale when you're doing a for loop, of 100 or 1,000 or even 1,000,000 operations, when you start doing that over billions and billions of operations in high frequency, it becomes an issue. And lastly, the data governance and security that was mentioned on the previous slide. We look at the other aspect of it, so like not the human behavior part of how we operate with the data, but more about the actual physical parts of it, like databases are preferred to CSV files. They secure, they've got passwords, you're already protected. So the security capacity of that. Again, like if I was just to like look at like Google Maps, I could see, so I'm a user of Google Maps. There's another billion people on the planet, and everywhere that I travel, Google's kind of like tracking that. They know my whereabouts. They know the length of the time of the journey. They know what transportation I've taken. They know where they started and know where I've ended. But can they anonymize that data and use that data in a responsible manner? So there's the whole large part of that. And if they can't, or if they're seen by the public to not be able to do that kind of thing, then they're all of a sudden people lose trust in their system. So that's a very, very big part of it. So we move on. And again, to know the differences, it might help to look at the similarities. And I think this is possibly the last slide that has a lot of words on it. So I'll read out the slide, but again, I've kind of like highlighted the key parts of this in yellow and orange and blue, and they all form parts of the latter slide. So, if you're taking anything out, just take out the highlighted parts of the slide. But data engineers and data scientists are two different roles that often work together to solve problems using data. Whilst data engineers and data scientists are often work on similar problems, their skills and responsibilities are distinct and complementary. So in a way, that's saying that the skills are different, but they also match up together. Data engineers build the foundations for the data science work, while the data scientists use those same foundations that have been built to generate insights and make data-driven decisions. So in some way, we see these two disciplines working nearly symbiotically in some kind of way, but not. Some people may argue that they're like completely different and segregated, and in other cases, we're saying that they're linked up. And as we go through the slides, we'll just see some more of this. So moving on, foundations. Data engineers build the foundations for data science work. That's effectively what they do. Data scientists, they use those foundations to generate the insights that make data-driven decisions. So we have one effectively that appears to be leading the other. On the latter slides, I'm actually going to, I could have flipped the roles around, who leads who? Is it the data engineer that's leading the data scientist because the engineering had to be built before the science was done? Or is it the data scientist that leads the data engineering capacity because the data scientist makes a demand, I need this kind of thing to be done in order to complete my data science, and the data engineers then set about constructing a solution that gets it together? Or is it just a complete ecosystem of the two that kind of like patches them both up together, and they're in some way operating together? Nonetheless, outside of that, what we can segregate is that the data engineers are building, what might be construed to be the foundations, and then the data scientists are taking the resultant portion of that, and they are using these foundations. And the ecosystem in total is just trying to generate insights and make data-driven decisions, and that appears to come from the data scientist side of it. So as per the slide before, really, and I actually only slipped this slide in earlier today, but nearly the question is which came first. It's literally a chicken or egg type of question that we can ask ourselves, but which came first, the data engineer or the data scientist? On the one hand, the data engineer is making components for the data scientist, and the data scientist is using those components. But if we were to go back in time, like right back to maybe the Roman times, even the prehistoric times, like caveman times, for example, or like Mesopotamia, like the ancient Egyptians, they never had computers. They had, like, before paper was even invented, they had to, if they wanted, or if the data scientist, if such a role even existed, you could argue they never existed, but if somebody wanted to record their data in some way, or do some calculations in some way, they would have had to use a tablet, like a piece of rock, and carve something into it. It'd been a slow and laborious process. Maybe in that very simple sense, the role of the data engineer was to make a more easily malleable rock, or like invent chalk, or create another invention that assisted that. So these things are kind of like working together, like this demand for something and this necessity to create, or just operating it. And then you come along with paper and pen, and then you come along with something like a cassette, which is now in the realms of our lifetime, at least, because hopefully, like, some of us still know what cassettes are, but like magnetic tapes, effectively, that were storing our data, floppy disks, and so forth, like again, like keeping data. And as we have those things and the computational power increases, and this is something that's driven from both sides of the chain, whether it's the data engineering side or the data science side demanding it, both of those are somehow symbiotically working together, and now, like today's age, where we've bypassed all of that, we've even moved past CDs, we've moved past like pen drives and other things, and hard disks, and now, like, if we talk to like the latest generation, we're already in the cloud. So our data science and data engineering is really talking about cloud technology, and it's like, how can we do that? How can we do it on a big scale? And then can we leave some models in the cloud, for example? And that'll be a data engineering role. So the data science model is left sitting in the cloud, and you should like go and pass your query in, maybe from a mobile phone or a lighted device, and then this you pass this like light amount of data in, and a heavy amount of crunching is done on a remote server somewhere. So when we say the cloud, we mean a remote server somewhere. So the data science part is nearly now fully integrated into the data engineering capacity, both in terms of delivery of the data, the processing of the data, and then that goes into a data science aspect, and then back the reverse channel of passing back the processed data back out, and sort of like delivering that to the end customer. So who came first question, was it the data engineer or the data scientist? Like, how did that grow? Well, I'll kind of like leave that for everyone to argue, or maybe a Q&A at the end. And again, like something, as I was writing the previous slide, I was kind of like, can we give examples of this type of thing? And maybe like an example that's possibly relevant to many of us was, and this was before keyboards were invented, but just something that you may or may not use naturally on your phone without even knowing about it in some cases. But when Swipe first came in, and I just cast in my mind back, and it was around the time of BlackBerry. So BlackBerry was an old type of phone, and an iPhone and Android phone started coming in with the touch screens. All of a sudden, you had a soft keyboard instead of a hard keyboard. And that's very much, and this is a classic example of where both disciplines have combined to produce a technology, because on the one side you've got the engineering aspect of the glass and the touch screen. When you touch the screen, can it affect the keyboard? But the other side, we see this swiping capacity, where, and I'm hoping that you're all looking at the slide, because I thought initially it spelt out a different word, because it's got the letters THIS, which is this, but if you look at it, it might spell out a different word as well. But nonetheless, it's kind of like, how does it get that prediction? So does it work, and how closely can you do the swiping? Like, how near did I have to get to the I for this to be a this rather than thus THUS? So like, that's a data science bit and a data engineering bit kind of like combined together. And I'm not sure at that point if we can see the difference between the two. That's a point where they're very closely aligned. By the same point in time, if you walked into Apple's offices or an Android office and asked the different employees, like what they want, a data scientist might just be like, I'm very much focused only on the data science part, and I'm only looking at the curvature of that line. And the data engineer on the other capacity of it will just be like, I'm just looking at getting that swipe thing down onto a keyboard, and I don't care about any of the data science parts. So like, they might split it, you might put it together. And then we move on from there, and this is kind of going to be fundamental, I guess, or like it's a massively core thing, which is the humble database. So we should like consider the database and like where this lies in everything, because the reality is it's so much a central part of it. Maybe, I guess the clue may be in the word data, but in some way, like, everything is coming out of this like central storage unit that we've done. Now, we don't have to have a central storage unit. We can have a decentralized unit, so we can have something now. And this is going to be a new question. Maybe we'll ask this question in a different way, but we have Bitcoin and other decentralized technologies that are coming out, and there's a whole field on apps and like the decentralization mechanism. We no longer need like central bank types of things, and no longer do we need like this central one central user database. It could be like a whole bunch of nodes, but nonetheless, we're still going to have in some capacity like a data engineer on one side of it and a data scientist on a different side, or at least maybe on the same sides, but interacting with this database or this decentralized version of a database, even in different capacities. And the data engineer is looking at like maintaining this and the integrity of the system, whereas the data scientist is kind of like looking at the stuff that exists within it. Can I take the magic that has been put into this box and like this unstructured or like randomish type of data, or even this structured data, and can I either structuralize this unstructured data and draw some conclusion, or can I take this structured data and the same thing, draw some conclusion and make some predictive analysis? But one way or another, that kind of like separates the components of the two sides of that coin. And then we look at the people themselves. So people, whilst the roles are different, due to limited resources, they are often shared by the same people with the same end goal. And the question is, what do I mean when I say like limited resources? And we will go into that. So we kind of like, we look at like organizations of companies, or like the resources could just be like the resources on your laptop, but it doesn't just hold itself to like the computational type of resources. It's also like if we look at companies or people, we have a certain amount of time, we live for a certain amount of time, we have a certain amount of time in our day, and things that we can do, and there's only so much each individual can do. So this struggle amongst this myriad of like or the resources that we do have is kind of like a joint effort, and that's a joint effort between data scientists and data engineers amongst a whole host of other people, but we're just looking at the data science and data engineering part of it. So we go from the people part and we look at companies, and all companies require both a mix of data engineering and a mix of data science. And I've just pulled this up. I pulled it out of Google, but in 2023, that's the current sort of like top 10 tech companies. It's not the top 10 companies in the world. It's sort of like top 10 of what are perceived to be companies are in the tech space. And we might have considered, for example, I don't know, maybe, for example, like Microsoft or an Apple, they might be quite good examples, and maybe even Google to quite a large extent, of being just companies that require data science people only. But the reality is that's completely untrue. They need a vast amount of engineering, potentially more engineering than science. Their data warehousing, their delivery, their operations, all of this kind of stuff. And like I went into sort of like the Google Maps thing, but like, if you went into Google search, for example, and looked at the same kind of thing, there's a whole bunch of stuff as how do they perform the search? They need to perform millions of searches very quickly. They need to record the data, pass the data into the system. So there's all the mechanics of that, also the engineering capacity, and then how and what they do with the predictive parts of it, or the AI component of it, or any of those other scientific parts of it, what they do with that data, and in order to construct it in a way that it has a use to someone else. And that doesn't just apply to Google, it applies to Apple. It certainly applies to companies like Amazon and Tencent. NVIDIA will use that information in a slightly different way, because they are more from the engineering perspective and the data science perspective, but nonetheless there. Tesla might be a half mix of that, the way that at least the company sells itself. Same thing again, we go down, we look at Meta, which was the old Facebook, and that might appear to be very much a data science operation, as all of these social type of platforms appear to be, and that is quite true to a large degree, because they're connecting people, and there's a huge amount of science that goes into it. But the reality is again, when you have a company that's got billions of users on their platform, managing that is an engineering challenge and not a scientific challenge, and it's a non-trivial engineering challenge. So it's quite a large thing to do. So that's from the company aspect of it. And then we move on. I take all of what we had before from those initial kind of paragraphs and the comparisons on the side by side in columns, and try to put the keywords into a Venn diagram in some way, like sort of like, can we segregate the two, and to have these components of data engineering and data science very segregated and apart from each other, so that in a way that we can say, oh, this is very well defined, this is definitely data science, and this is data engineering. And kind of like as I was doing it, like the reality is not really. You can sort of like push things more to one side than the other. So design and construction, you can certainly say that that's probably, we could all agree that that's probably more of an engineering type role when we're talking about designs and constructions, rather than a data science role. But we can also see that there's going to be a scientific component to it. Likewise, we move down one and we go to like scientific methods, and again, like we tend to think of that as being that's going to fall into the data science part quite largely, and so it makes it into that circle. But again, it overlaps, it falls like the minute we start talking about methods, we start talking not just about science, but a component of engineering, because we want to enhance these methods. We need to speed these things up. They can't operate it in a slow manner, not when we want to work with big data. So when we're working with small data, that might be purely like what we might consider to be a data science part. The minute we start doing something intensive, so if it's either big data or fast data, so high frequency data, so something computationally intensive, it starts migrating away from data science and into data engineering. So the boundaries initially might have been clear, but then they become a bit phased. Extraction of knowledge, you can kind of like pass maybe into the data science component of it, because that is what data science is trying to do. It's trying to extract knowledge. And likewise for data engineering, its focus is on extracting data. Its focus isn't on extracting knowledge. It's the knowledge of extracting data, you could argue, but the reality is that data engineering is for extracting data. And then programming skills, it fell into the data science category, and we'd certainly argue that programming skills very much are a key component of data science, but I've never seen a data engineer in any engineering that I've ever done. You've certainly needed a whole host of programming skills. If any, you might have needed a plethora more of programming skills because of all of the architectures that are out there. But that falls into data engineering, and the difference between those is the types of programming skills that you need. So it isn't a question that you need programming skills in one or the other. It's more a case of, we could have split this up into sections of, what type of programming skills you use. And the data scientists, at least nowadays, tend to go for Python. It's become like the child adopted language of data science, because of its ecosystem in other parts, and maybe in part because of its simplicity to use. But then there's other capacities. So when we sort of that doesn't mean, by the way, that there are that the other languages don't suffice for data science, because Java does, Node.js does as well, and a whole bunch of other ones, and C++. But you might argue that their fortes, for example, C++, falls more into the data engineering side, just because of speed, and it's closer to the operating systems of computers. So it's more like speed of operation. And then we've got mathematics and statistics, and that's kind of like the verse. I should have put statistics. Maybe you can push statistics to the data science side, and even then, you need a whole host of statistics for data engineering, because you're measuring a lot of the stuff that you're doing. Mathematics, again, will fall into both, and maybe some kind of engineering maths as well. So like some sort of applied maths falls onto the data engineering side, possibly a bit more than the data science side. And finally, setting up a pipeline, we might argue at least that probably falls into the category of data engineering. Pretty kind of like strongly. Again, it's one of the things that the data engineer is trying to do. But again, you can envisage capacities where there are pipelines that are necessary as well for the data scientist, because once, in order both to get the data into their system, but also like producing this data is like not necessarily a one component, it's a multi-component process, and there needs to be pipelines between those multiple components, and those are the pipelines I'm referring to for data science. So there is still a pipeline, and you need to deliver an output in some way. So how do we get that out to the end user? So we take the data science components, but they're not just for data scientists. Scientific methods, data engineers need to understand the inner workings of the core models, and that's why they're not for data scientists. So there's going to be this overlap. And programming skills and mathematics, data engineers, again, they need different programming skills and different maths, and in particular, they might need mechanics. But nonetheless, like, there is a leakage from the data science components that aren't exclusive to data scientists. Maybe I talked about some of that on the slides. So, like, and here's just two of the examples I've kind of like pulled out because they sort of like stand out as being obvious examples. So, and in particular, the inner workings of the core models for data engineers, because you're not going to be able to produce an engineering solution, or at least in order to be able to produce an engineering solution, you need to understand intrinsically, often in cases, the models themselves, like how they're working, so that we can sort of like bypass them. The last thing that we want to do is kind of like put something into a for loop that could have been outside of a for loop. So that kind of very simplistic thing, because all of a sudden you've created an overhead to your operation, like literally with one line of code that ended up repeating itself like millions of times unnecessarily. So those types of things, and you'd only garnish those if you have an understanding of the inner workings of these models that are used. So, and likewise, if we take the data engineering components, we can say they're not just for data engineers, and we can pull out a couple of those. And one of those that stands out is design and construction, because a data scientist needs to understand the design and construction of systems for efficiency purposes. They need to know what they've got to work with. there's no point in the data scientist creating a model that isn't catered for within the system. And you could pull out very simple things like, a company had a database, and a data scientist is kind of like expecting to pass their information out on a CSV file. And that won't happen. Now there's a challenge, and in some way that needs to be fixed, or the code needs to be written in an efficient manner to fit into its next part of the process. And that probably leads on to the automation of flow, which is part of, or the next part maybe of design and construction. But the data scientist needs to connect into the automated flow process to receive the benefits of the automation. And that actually goes on the receiving part of it and pushing data out. In some way, like, we need to, and from the finance world, at least, if I cast my mind onto trading, I've got lots of vendors that are supplying information into the system in the format of trade data, trades that have been executed, and some of those formats work, some of those formats don't work, and it's sort of like you need to make them all work and gather as much information as possible, and fitting that in somehow into your system for the purpose of decision making, so that you can then produce some kind of output. And again, these output models are written in different parts of the company infrastructure to the inputs of the data. So you've got like 1, 2, or maybe even 3 or 4 levels of processing in between, and you've got to be able to move between each of those layers. So there's very much a flow process that happens in this operation. So we move on, and we look now at the ecosystem. So the ecosystem of data, science, and engineering, and I kind of like separate them now. And data is the core part of it. And this is a very small aspect of all business, but nevertheless it's an aspect. And right in the middle of everything sits the data. And then on the one side you've got the scientists, and then on the other side you've got the engineers, and they're effectively operating on the same thing. Nearly, maybe, I don't know, like 2 surgeons operating on a patient, fixing different body parts, but like they're both working for the same goal of fixing the patient. The data kind of like lives in the middle, but the reality is they're not just only, the data scientist isn't only working just on data. He's got other things to do, and in other fields there might be other things to do. And the data engineer, likewise, they aren't just both working only on data. So at the boundaries, at least, they're also interacting with themselves. There's things outside of the data zone. So if we were to talk about kind of like, I don't know, maybe if you were to take petrol cars, for example, or like you were trying to fire a rocket up into space, and you were to look at the fuel inside of that, there is a lot of data. So there's certainly a lot of data science. There's certainly a lot of data engineering as well. But it's not only data. You're now also looking just at science and engineering, because you're looking at how rocket fuel behaves, within the model itself. So like, can we get our spacecraft into space with the amount of fuel that we've got, the weight, the gravity, and so forth. And whilst the data bit is there, but the scientists and engineers have historically always had to work with each other, with or without the data. But obviously the data is an integral component of that system. And this is just generally how the system looks. You could draw the picture a slightly different way or something, but generally speaking, that's how the data science and engineering ecosystem, broadly speaking, might look to us. And then connected and disconnected is the title of this little slide here. Whilst the segments are different, there is a heavy connection and reliance between the 2 disciplines. So we could ask, are they connected? Are they disconnected? We don't know, but what we know is there is a connection or a reliance in some way between the 2. Data is fed and rotated between the data engineers and the scientists. And one thing that certainly happens is these iterations in this process, who's ever started the process, and it might not be started by one side or the other, but like it might just be driven by the system, but in some way iterations are happening to continually evolve this process. So we're going to improve it, and goes through like these cycles of improvement until the next layer comes about, where we get what we might call like a master step, or like a great leap forwards. And there's been a few of those. And the system itself is basically, we're seeking these structured solutions, and it nearly needs these components, whether they are separated or whether they operate together, they need to kind of like be in the same, they are operating for the same greater goal, should we say. And we move on. And this is the continued and discontinued chart effectively. And effectively, you know, if we were to draw out like what we might consider to be some type of cycle of how this would operate. On the far left hand side, we have this like unstructured data, and I was kind of like very careful to sort of like make sure that the data science and engineer components are in there, because you get this unstructured data, and there isn't really one that harnesses the other before. Is it the scientist that goes like, oh, I've got this unstructured data and they need to do something with it and I can't? Or is it the engineer that's just collected this unstructured data and go like, here, I've just collected a whole bunch of stuff, go and do something with it? Nonetheless, this unstructured data makes its way into the ecosystem in some way, and it gets fed through. So it's either, you know, made its way by the data scientist or the engineer, and it's like, we've got this data and it goes through, and we go through an iterative process and some work's done on it, but that work wasn't sufficient enough, and it needed to pass back through to more engineering to be passed into another model for another iteration of the improvement. And when that model was complete and sufficient, and so like we upgraded our systems, we went from like 2G to 3G, we're able to do a bit more, and the science was enables we could do a bit more science on it and get a bit more completeness, and take one more step forward. And then we needed another engineering process to come out of it. And after that, we move back into the science part of it. Can we harness, can we take some more knowledge out of the system? And as that process keeps going on, the unstructured data on the left-hand side, this stuff that we just kind of like generically connected, this real world data, we could even call it, like when we say unstructured, it's just stuff that we're taking. So, you know, the weather, the environment around us, any of those types of things, you know, even like social media or our behavioral patterns, any of that. It's all unstructured data, and we're taking this out, and companies tend to do this more than anyone because they're monetized to do this, but they're taking this unstructured data and they're structurizing it, you know, they're structuring it, and they're getting some conclusive data out of it, and they're producing like results and predictions, and they're selling that back on. Or they're passing that back into the system, this structured data. Like all of a sudden, kind of like I've measured the shopping habits of like all women that go into, you know, a specific shopping center at this time, and they all tend to buy you know, more handbags than they do shoes. So the handbag shop should be let's advertise this to handbag shops that you want to be there, you know, in this particular one. And then in another shopping center, like, you know, or in another area, like shoes are more products, so you want to like sell this one to this thing. So all of a sudden you're able, with this like big mishmash of data, to target a demographic, measure things in certain ways. And there's a whole variety of ways that this kind of stuff could be used. You know, you could take it out to the sort of like the energy companies and how they behave, sort of like, you know, measuring you know, their ecosystems, and is there like is there a big oil well here, and so like, you know, let's do that measurement. Can we improve our systems? Can we get our feedbacks in place? And the better that you can do that, the cheaper the cost is of extracting or discovering your new oil field somewhere. So all of these processes are done we're doing them for our own, we could say selfish benefits, but we're certainly doing them for our own benefit. And that's it. So let's look at the process components, and we look at the typical major sectors, and I've kind of like as I was talking about the slides anyway, I sort of like, have given examples. I've given a couple of financial examples and manufacturing, but the reality again was when I've pulled this out and I sort of like, initially sort of like Googled it or stuck it into Chat GPT to sort of like have have a look at like what are the sectors. There's just too many of them. So I just go like, let me get a list of what might be perceived outside of my own personal views of what are kind of like the major sectors. So the top one came up as being manufacturing. So that's, just making of objects and all kinds of stuff like that. Then we've got the energy sector. That's kind of like why related to, the oil companies. It's a humongous sector. Healthcare, we can imagine a whole variety of places for healthcare where, where this would be applicable. And, for the healthcare side, it's actually quite interesting because you're dealing with people. So when we're talking about it, you have got the measurements of vast numbers of people. Like, so if you're in the 40 to 60-year-old category, what kind of heart rate should you have compared to somebody who's in the 60 to 80-year-old category? So you've got that type of data, which is quite scientific. You've got to behave in a certain way with it. But at the same point in time, you're actually collecting personal individual data about people, so about individuals. So you have to make sure that that their data is maintained and kept safe for them, secure, password protected, because they want to keep their own personal details for their own reasons. And the same thing in a way, actually, like in parts of it falls into the financial services as well, because while there's a whole bunch of things like global trade data and so forth, that's quite shareable and autonomous, and our concerns are just kind of like delivery and passing that information between the various components of the integral system. At that same point in time, we've also got the end component of it, which is a banking. And again, people don't want their bank accounts or something. They've got security there, and if those types of things are breached, while they wanted to connect in and be passed into as many systems as possible, because they wanted to go into the shop and do their shopping and have it all seamless and pay with a credit card, that was all fantastic. But at the same point in time, they don't want their credit card to be breached and for their account to be emptied by a bad actor. So we have all of these different sectors that are involved in, but there was a whole bunch more of them as well. So these are kind of like just the top 5, and like we're going to look at, so like how data science, or you can even think about it for yourself, but how data science falls into certain parts of that, and data engineering falls into another part. And you may you might be students, and you might be someone who's already practiced in one of these fields, and sort of like have a very clear and defined idea about which one is a science and which one is an engineering type of role, and they might be that might be very obvious to you. So we move on. We're just going to briefly touch each one of those, just by way of example. But again, like in the comments afterwards, maybe you might want to have some input into this kind of thing. But if we look at manufacturing first, its sector includes the production of goods such as cars, electronics, and clothing. So you can sort of already see where this might be heading. But all I'm going to do in each one of these is kind of segregate them. On the left-hand side, I'm just going to put 3 things that might be data science, and on the right-hand side, 3 things that might be data engineering. Break them out into 2 parts, and I'll do that for each sector. But on the data science side, you're looking at things like material, sales, costs. So all of the inputs that are coming into your data science, things that we want to measure, because we're going to use them for the analysis of data, right? So that falls into the second part of data science. But we want to we want to get this that we want to know what information we can get and how we can use it. And then we're going to start to use this data with some sort of analysis. We're going to produce whether it's a complicated AI type of system, a machine learning thing, or something much more simplistic, so measuring and just getting some basic stats out of the system, like means and averages or something like that. We want to get this kind of stuff, sales data, but in manufacturing, it's how many blue shirts were made, how fast can we make them, how many are we selling, that kind of stuff. And So we've got all of this data, we're getting it all in. This is all the data science part of it, and you know, how we can just sort of like break that down and put it into a couple of charts as like a user dashboard, and give it out to effectively like some decision makers or the CEO, so that they can sort of like see the way their ship is sailing and kind of like guide it using these dashboards that are given to them. You know, if it's really easy and really cheap to make loads of red shirts, and it's quite expensive and laborsome to produce the blue shirts, and also at the same time, if it's if all of the red shirts are selling really well, you know, your user dashboard will show both of these things, like lower costs and higher sales, and it will be very obvious once the analysis of what was once this kind of like semi-unstructured data, it would be very obvious which one we'd want to pick. Quite often it's not as simple as like blue shirts and red shirts. Unfortunately, it's a bit more complicated, but that all falls into the data science part of it. But the same part for the data engineering side, we've needed to get these data inputs. So, you know, so how can we get this kind of stuff into the system? That's a challenge for the engineer. And again, and we're going to see this like repeat itself on the other slides, but like processing and storage. So again, it's the computational power, the systems, the infrastructure, everything that goes around it. You know, how we store the data, how we use the data, how fast we can do all of this. And finally, the assistance with the reporting mechanics. So we've got our dashboards and things, and kind of we want to be able to deliver this to some people. Are we delivering it on a web technology? Are we delivering it on mobile phones? Like, so like, are we keeping this thing internal behind databases? Like, you know, so are we sending out PDF files as reports, emails? So all of this other kind of stuff that sort of like fits around the actual data science component that was there. So, and we can see the distinctions are beginning to, you know, to sort of like manifest themselves at least. So we move on to the energy sector, and this includes the production and distribution use of energy, such as oil and gas and renewable energy sources. Again, you could add in a whole bunch of things as well. So like nuclear energy or so forth, you could throw in a whole bunch of other things into there. But the data science part of it, it's going to look pretty similar to the previous one and the next couple of slides. We're looking at materials and sales and costs and inputs and that kind of stuff. So the input into our scientific models that we have. Again, whatever we're doing with this, whether the complexity is quite simple in some cases or the complexity is quite difficult because the signal to noise ratio is quite hard, and you know it's more difficult to like identify it, or you know, we want to just beat our competitor by that small margin and we need that extra bit. There's an analysis of the data, and without a shadow of a doubt, the user dashboards, the outputs are nearly going to be there again, because that's ultimately what our original goal on the data science part of it, which is, you know, where is this oil field? Which is the best source of energy? Like, you know, how can we enhance ourselves? Should we pick nuclear? Should we pick gas? Should we be clean? Should we be renewable? What is the cost of renewable? You know, can we measure all of those types of things? And on the other side of it, again, you've got like, and it kind of like fits in nearly, but for the data engineering side, we're again going to be taking in data inputs. They're only just going to be different types of data inputs. They're going to come in different formats. So you know, you might be measuring like an oil field, so it's an engineering challenge, and then passing that signal back out, you know, the depth of an oil field, and you know, the ease of extraction and the pressure within the well and those types of things. So that might be an automated electronic process, or it might be a different type of process. Then again, we're going to have the same issues, just manifesting themselves into a different sector in terms of processing storage. Yeah, a lot of the large companies will use a similar type of storage strategy, like, you know, what is the latest and best out there. You know, so it would be big server and cloud type of things now is where everyone is tending to migrate towards. And then finally, we've got the reporting mechanics again for the engineer, and that's the same type of thing. Is how we fixing all of this together to sort of like pass it out into the systems that are necessary for all of the key stakeholders. You know, the CEO, who wants to just receive this on his mobile phone, or someone else who wants to receive a PDF file, or an investor, who wants to kind of like get the 400-page British Petroleum report, that kind of thing. So we move on to the next slide, healthcare. This sector includes a provision of healthcare services and the production of healthcare products. The most important part, or at least the key differentiator in this part compared to the other ones, is here we've got people, and we're literally like talking about the patients effectively in the healthcare part of it. And the maintenance of the, like the costs and other stuff that goes into there. But we're recording human data here. Like each one of these, or anyone with this pulse, or with this demographic, or with this age, and so forth, they're actually real people. That's like us. And I may or may not want my data shared with people for like a whole bunch of reasons. And then again, we're going to go into the analysis of this data. So like once we've taken the people part of it out of it, like, can we spot some trends or something like that? For example, I don't know, if we go like take the south of England and the north of England, it's like it's healthcare, like more people dying of heart attacks in certain regions, or do more people have bad teeth in certain regions, like in the towns and cities, or places where water is being treated? Are their dental tooth care like better or worse? For example, like it tends to be better where fluoride's being injected into a system, but those types of things you only get on like a larger sort of scale, and you need to have measured it on tens or hundreds of thousands of people to like observe these patterns. And finally, from that, same thing, the user dashboards, all of this kind of stuff, the demographic charts, and all of these sorts of things that we could plot. And we could go down to things like, again, we could just pull out COVID. It was recent. A lot of the scaremongering, should we say, or confusion, is like the number of deaths are involved. And if you sort of like looked at the demographic of the types of people that were dying from COVID, it tended to be people who was like 70 and above and not below. So one might have argued that they already had these underlying healthcare conditions, or they were already kind of like frail or towards what one might perceive to be end of life in terms of average life expectancy, which again is a data science thing. In the Western world, at least, it's somewhere between 80 to 85 years, depending on the country. So like in the UK, it's like 82 years. The 95-year-old that died of COVID, did they, one might question if they actually died of that or not, and so forth. So there's those types of things that we need to consider, and a user dashboard would have been helpful for that type of thing. And like again, the data engineering part, it's going to operate in a similar fashion. It's going to be accepting of the data inputs for the data engineering capacity, like the data science bit. When you've got people involved, it's going to be slightly different. It's going to be slightly more of a challenge, because all of a sudden you have all of the same things that you've got before, but you need to behave in a responsible manner and in a secure manner with the inputs that you get. The processing and the storage, not so much for the processing, which is fine, it does its thing because you've anonymized your data by that point in time, but certainly the storage of it, you don't want all of people's private details to sort of like be leaked all over the internet or something like that, which tends to happen from time to time. And finally, the reporting mechanics, that behaves again in a similar sort of way. You do need again to sort of like need to take care in some way. There was something actually in the newspapers recently, I think it was for Christmas, where a company, but this is like just a very, very like funny example maybe, but it delivered all of its patients a report saying that they had some sort of like cancerous condition, whereas in fact they actually meant to send them like Christmas cards. So like instead of wishing someone festive, like there was clearly a breakdown in some capacity of what you might term to be the engineering component of that. So just things like that. And then financial services, this is a sector I've been involved in for a long time, but it includes banks, insurance, and other organizations that provides financial services. There's a whole bunch of things that go into here. But, so I actually transform this, so just put revenues and costs to keep it really simple, but it's way more complicated than that. I've literally just put in 2 words that describe, like, literally, you might need like 60 or 70 words. But of those things, we thought look at effectively what might be a top line and a bottom line. We do our processing and analysis. We're trying to predict, we're trying to guess, we're trying not to lose money, we're trying to preserve money, and then we're trying to make money. And we're using data science for this, and the dashboard, again, like the analysis of the data, it might not go into dashboards. We might just feed it back into our system, in which case it goes into a data engineering aspect of it to do more data science. But we might sort of like create dashboards, and like if anyone sort of like logs in and you look at the FTSE 100 or the S&P 500, you might do something as simple as a heat map. And that's a combination of data science and data engineering, but the heat map component of at least the colorization of it, like, so like red for everything that's gone down in a day and green for everything that's gone up, and some kind of mixture. You can sort of like see these patterns that occur between the approximately 100 companies that are in there, relative to the sectors and news that happened. And some days everything's all green, and other days everything's all red, and sometimes it's sort of like a mixture of the both. And you can do these types of heat maps and stuff like that on that. So that's just one example of many hundreds of examples that I've used over time for the purpose of data science. And likewise, again, data engineering, it's a challenge of accepting data inputs. There's tons and tons of vendors vying, to give, like, sell their data into the systems, and you need and the structure of doing so. You have all of the same types of processing and storage issues that you have on the that you had in the other sectors. So all of that type of stuff, the processing is massive, because all of a sudden we're talking about not only is the data big, but the frequency is quite large. So you want to like repeatedly do some kind of process, like an index calculation is an average. And in some cases, like an index calculation might be the average of 2, 3, 4,000 securities. So you're sort of like taking an average and a standard deviation and doing this thing. And whilst that seemed to be simple initially, like when you start to want to do that multiple times per second, all of a sudden that becomes a challenge, a huge challenge. So I could easily ask you, like, can you get me the average of 100 numbers, and, to do that once every day? Not a problem. But can you get me the average of, like a few thousand numbers that are moving continuously with live data feeds every second, and to like do that same process? All of a sudden it's difficult. And the reporting of that as well, it's going to, like, are we talking about real time or static end of day reports and so forth for decision making and for actually transacting? So a whole bunch of stuff in financial services. And the last sector here, I think, on the list is technology. This sector includes the development and production of computer hardware, software, and other technology products and services. And in many ways, actually, the technology part of it is nearly like a feedback as to part of the system, because this is a component of the system that's sort of like producing a lot of the data science and the data analysts in the first place. So it's kind of like we're working with ourselves to improve our own selves. But if we look at it like just from the simplistic perspective, you've got revenues, and what I've put is techware, which is because I couldn't fit everything into one word. So I've invented this new word. I don't think that word exists. Techware is hardware, software, and other technology. So I bundled them all into one word. So all of this kind of stuff that comes in, and then the costs. And you've got the same issues, you've got the same analysis, and it goes in a whole bunch of different ways depending on the technology, what you're trying to do and what you're trying to achieve, and then pushing this kind of stuff out. So you could just be Dell computers, so like building desktops back in the past, and then desktops stopped being of relevance, and mobile phones came about, and if you didn't spot this trend, your business was going to be doomed. So that kind of stuff. And then we go into the data engineering side of it, and again, accepting data inputs. You can imagine, like, so I don't probably need to go into too much, but the processing and storage of data, Again, it's going to be a very, very big operation. Think of big companies, don't think of small operations anymore. And finally, the reporting mechanics. So that's all part of the technology aspect of it. We look at now the process and components. So we look at typical processes in the major sectors. So we've got manufacturing, energy, healthcare, financial services, and technology, and many more industries, as I said earlier. And we just tend to see a common theme. And we move on to this scale part of it. So how data science and data engineering looks for small, medium, and large companies. And what do I mean by small, medium, and large companies? So we could kind of like just crudely lick our finger and stick it in the air. It's not like it's not set in stone by any way. But a small company, one might argue, is 1 to like tens of employees, so not that many employees, like a small office that you know might be used to, like a small family office or something like that. A medium company might be kind of like something a bit larger than an office. It might have a few hundred employees, so all of a sudden you got 100 to a few hundred employees there. There is no like hard or fast boundaries, 50 employees, a small company or a medium-sized company. But we'll see something that comes out of this for sure. And then finally, like large companies, which are thousands or more of employees. And like I worked for one company, Mizzou, I think they had 250,000 employees, I believe it was. So 250,000 people. It's a large operation. It's more like a small army than a company, if you think of it that way. And we're going to see something that manifests itself out of these, when we look at the scale of companies and its role on data science and data engineering. So if we do take a small company and we look at it's 1 to tens of employees, so like just a few people that are in a company, a couple of friends starting something up for a startup business. Every employee has to muck in and assume many roles. And and when I say that, I kind of like literally mean like every employee has to muck in. So the CEO is also kind of like the guy that's organizing the shelves, or like the CFO. He's doing the data finance and the data engineering as well as being a CFO, because there is only like 3 people. And I did work in I've worked in some places that got like tens and hundreds of thousands of people, and I've worked in other places where it's literally been like 1 or 2, and we've been asked for like an organogram, a chart of the organizational structure, and it's just been 2 people, and it's kind of like, who's the CEO? I'm the CEO. And then like, who's the CFO? Oh, I'm also the CFO. And like, who's the money laundering officer? Oh, I'm that as well. And who's doing this component? Oh, it's the other guy. And there's only 2 of us, so it's kind of like, that's an example of a small company. You basically have to do like, or one person is going to have to do like quite a lot of roles in a small company. The tech guy will be the guy where so it'd be one person who does all tech, so he sets up the computers and networks, and he happens to also then be the data scientist, because the other guy happens to be on the legal side of it and doing other things, so doing legal and sales and other things. So all of a sudden, when you start asking this question, the difference between a data scientist and a data engineer, they're the same thing. So you ask somebody in a small company, the data scientist was a data engineer. And that person will be the go-to person for all of the technical issues. So we move on, we go to medium-sized companies. Medium-sized company, hundreds, it's got hundreds of employees. So my little picture in the top bit there, it's got a few more employees. And all of a sudden, when you've got hundreds of employees, the employee roles are more defined. People are allocated to specific parts of the process now, because there's enough people to be allocated to specific parts of the process. They'll begin to specialize in their own expertise. So you won't have to have, for example, the lawyer also being in charge of head of sales. The lawyer will be doing lawyer stuff. And the head of sales will be doing things to do with sales, and the data engineering person will be doing all types of things to do with setting up computers and the engineering capacity of it. And you might even begin to have a data science type of role where the person is just doing reports and data science type of stuff. So all of a sudden we see this separation of roles. Something is being born out of this, and this is the growth of the company, and like the segregation of roles begin to separate. And then we move to large companies, and large companies are thousands or more of employees. So like that little picture there of the football field, I think it's a football field, it's an example of thousands of people. And all of a sudden, when we talk about these sorts of companies, the roles are quite well defined. They're strongly defined. And in fact, you'll get teams that are allocated to very specific parts of the process. So like a whole team of people now will be working on a data science part of it, and there might be little to no overlap at all in these roles. So like a whole team of people will be allocated to like the engineering part of it, and one person will just deal with databases, and another one will just deal with networks, and another one will just deal with another aspect of it, and the person that deals with databases, one of those will just be doing like the infrastructure of the databases, and the other one will be dealing with like the integrity of it, like the usernames and passwords. So even that will be sort of like split into there. And likewise, like if you walked into the data science part of it, like one person might be dealing with sort of like the coding bit, and then there might be a team of analysts doing mathematics, and sort of like all of a sudden these roles, when you come to this bigger company, not only are they segregated, but the science and engineering roles are like they're completely separate. And the data scientists will have, I won't say will have nothing to do with the data engineer, but their role will be very well defined versus the data engineer. So we take a look at this and then ask that question in a different way. So I've just titled this chart "Scale versus Skill." And scale is referring to the size of the company, and skill is not really defining the skill level, more so it's defining the component that you're kind of like set into. So if we take this small company, like right at the top of that tree, the data scientist is the data engineer. He's the go-to tech kind of person that does basically everything, whether it's programming, plugging the computer in, switching on the lights. He does the whole damn lot. Then we move into the next sector, which is the medium-sized company. And all of a sudden, you've got enough resources to start splitting people out. We're not just talking about data scientists and engineers. We're talking about all of the other roles that are involved in the company. People can set about doing their own thing that they kind of like specialized in or wanted to do in the first place. And the data science capacity of it is somebody, who's like literally like sort of like generating the ideas and like working on the data itself into like mapping a path for like the sales of a company or something like that. And the data engineer part of it is someone who's just dealing, maybe handling just the databases and the internet connections and the other stuff around it. And again, if we go down that scale, when we move to the larger company, it becomes quite obvious, right? There are thousands of people, and there's teams of people that are doing the data science role and the data engineering role. And in some cases, the data scientist is just very far away from what the data engineer does, like completely like help desk versus, mathematician. So like completely opposite ends of the scale. So that's a scale versus skill chart there. And then that sets the tone for focus. As a company becomes large, the focus on each individual becomes very specific. So data science is not equal to data engineering when the company is large. And when the company is smaller, the focus is on something much more generic. So all of a sudden, if you ask someone in a smaller company, they'll see data science as being equal to data engineering. So it depends on, now that question that we've asked, like the difference between the two, is literally, you may as well be asking the difference between the size of the companies. from that capacity, it might suit you to be in a small company because you like doing all parts of those types of things and be hands-on the engineering and the science part. Or you might want a very defined role in one small nuanced space somewhere, in which case, a larger company might be more suitable, where you're just like literally, I'm just focused on data science and nothing else. I'm just focused on, my passions in data engineering and the engineering side of it, and I don't want to know about the other part of it. So there's a big difference between the two on those things, and that comes from the company size. So in summary, large scale data scientists, DS, and data engineers are very different. But on the other side of it, from the small scale, data scientists and data engineers, they appear to be quite similar. Small companies, one person is doing multiple roles. Large companies, you're differentiated. Now we go on to the complexity, and it might be similar, or we will see that it's similar to the company size, but the difference between data science and data engineering diverges as kind of complexity increases. It's a bit of a mouthful of a sentence, but kind of had to put it in there. You might even have a small company, but it's got complex processes. So all of a sudden, the roles are going to kind of split out again, if that makes sense. And that's not to do with company size, that's got to do with the complexity of the process. So a complex process, we're talking about big data. All of a sudden, you start needing large servers. All of a sudden, your challenges start becoming engineering and scientific challenges separately. They're not one thing. When you go to like a medium-sized type of process, you've got a medium amount of data. Like, what does a medium amount of data mean, right? Possibly that you're on, instead of being on like large multi-scale multinational servers, you're on some sort of like local office server where you've got like, say, 2 or 3 or several offices, and then you've got one room that's allocated as like the server room, where there's a whole bunch of computers in there providing the server. That might be perceived to sort of like be a medium sized company, or one that's got the servers in sort of like in the room, but like in the back corner of the room. And finally, like if you've got like more trivial processes, so we're talking about small data. So all of and that could apply to a big company. So you could be a big company, like a massive like law firm, but not but actually not require that much in terms of data. So you're not like, there's no data complexity there. It's more like everyone's kind of like working off of local files. They're working off of their email system. They're able to save things on their laptops, and so long as their laptops are like kind of like relatively secure, their PCs, and they can like network into the office, that's kind of like sufficient at their level. They weren't ever seeking anything more than that. So it just depends on this kind of thing depends on the level of complexity. So we'll go and take a look at these. So if we look at like small data first, a spreadsheet solution might be fine in a small data solution, right? You can get away with Microsoft Office, that the Google Suite, LibreOffice, I've named a few of those, and you can get away with a small database. You don't even need a small database. You can just use like local files, CSV files for storing your data, and that might be more than sufficient. That will give you enough scale to sort of like do enough things. And all of your data science and your data engineering is all kind of like in one. It's all integrated into the PC, and now all you have to sort of like figure out is how I get my CSV file into my Excel sheet, or maybe some like piece of code, but like I just want to sort of like get this data, transform it in some way, do some sort of like simple operation, and then push that out, some sort of dashboard or resultant thing that I can kind of make decisions on, or decisions can be made at like this local scale. So then we move on to this medium-sized data, and all of a sudden the spreadsheet solution isn't sufficient anymore. It becomes insufficient. You start needing a bit of programming. You start needing databases, because you don't want local files to sort of like be flying all over the place, because it's like it requires a bit more than that. And if you did have those local files, they become too big to read, or like if you're reading multiple times, you'd have to keep on reopening the files multiple times, and that's intensive. Whereas you might now need a database that's got a permanently open connection that saves, that's an overhead saved. So all of a sudden processes are required that are beyond what you might take out of, you know, what we perceive to be our Office suite. So a database and code solutions with the potential to expand effectively is what you're considering when you've got medium data, because hopefully you're growing that into large data at some point. And then finally, you've got big data. And when we're talking about big data, we're talking about, think of big companies. So all of a sudden, you've gone from this small thing to this like big company, or this massive database, as much as you can collect. And even if it was a small company, but a company that wanted to collect as much data as possible, that's going to come at a cost and an overhead. So like, you know, how cheaply can you set this up? And both in terms of physical space and also in terms of computational time. So a database or some kind of farm or some kind of cloud computing, all of a sudden, the type of programming that you're going to do needs to cater for sort of like large scale efficient processes, rather than like it could have been inefficient and so like, you know, the passing of the files. It didn't matter so much if you weren't efficient with your medium-sized data. Now that's going to start hurting the company or your operations in some way. So you've got to consider this large scale, like bigger programming. There's all of a sudden also your science and engineering. You've got complexity coming into there. And it might even be a case where, you know, if you are a big company, you'd have committee meetings. And if you're a small company, you'd certainly have to like just figure out or have it documented. So like the processes that you were going to go through. So processing and storing meaningful amounts of data, you know, that can be expensive all of a sudden. So processing and storage are meaningful and expensive. So we look at the complexity scale and we see a similar type of thing where you've got small data. The data scientist and the data engineer, they're all raveled into one. They're probably all raveled into something like Microsoft Office or Google Sheets or Power BI or something like that. When we go on to the medium-sized type of data, all of a sudden this concept of what is data science and what is data engineering starts to segregate itself, because you're thinking of these things as operating differently. All of that, I'm now considering databases and servers and other parts to the operation, and I'm going to segregate them from the data parts of it. I've got enough problems, so like processing my data parts and what my algos are going to do, and pulling out the data and understanding it, and having that all working and operating and delivering me are like two completely different issues. So one's data science, one's data engineering. Now they might overlap at some points, but like, you know, they're but when we're talking finally about big data, there's just a big difference between the data science component and data engineering. It's all of your models and stuff, and any sort of like data science, any sort of like, you know, computational models, like AI type of things that you're building in your data science capacity, like, you know, what am I going to do, my analysis and so forth, are completely different to the data engineering part of it. Like absolutely completely different. Like, how do I store it, warehouse it, pull it, the speed of pulling it? Do I make this request to the internet? You know, how long is that request going to take to do? Or should I warehouse that data locally and operating on it in that way? They're engineering types of questions and not really data science types of questions anymore. So those roles now have been segregated when the data has become bigger. So as the companies become bigger in terms of number of people, we see this segregation. As the complexity is increased, or the amount of data has become bigger as well, those roles become segregated. So we put them together, complexity and size. Both complexity, that's the size of the data, and scale, which I'm referring to here as the size of the company, has the same effect on the similarities and differences between data science and data engineering. More parts, or like bigger companies, bigger data, so think of more parts as bigger, gives you this bigger difference, and fewer parts is going to give us a smaller difference between the two. We'll be able to differentiate between them less. Now we take just a real world example of applications for each role. And on the one side, we take data engineering. So data science, and what does a data scientist use? Typical things that I've used. And I never called myself a data scientist, so I didn't know that I was one. But I must have been one because I've used NumPy and the Pandas data frame and Matplotlib, and they're very much data science tools. On the other side of it is data engineering. Again, I didn't know I was a data engineer, but like there's huge things about processing power that I need to consider to get things working. Data transfer, a massive operation in itself. Like, how am I going to get, like, all of these things have kind of like hit me over the course of time, as parts of work. Like, they're massive failure points if you get them wrong, because it'll take down all it. There's no point having a good data science capacity if like your data transfer doesn't work or your processing power isn't sufficient. And you're always pushing on the boundaries of each one. So as soon as you've got enough processing power, guess what? You increase the size of your Pandas data frame, and now you're pushing on that boundary again. I want to do more computations now. And then finally, of course, the delivery mechanics. Sort of like, how do we get this out? Do I take this data, like what do I do with it? Am I taking it and doing something manually with it, or am I feeding it back into the system for transactions? In the terms of finance, half the time I'm feeding it back in for the purpose of transaction, and the other times I might be making human decisions. Again, like, people have a view on like, the percentages of each that you might do with that. Collecting and cleaning, which category does data collection and data cleaning fall into? That's kind of like, it's a bit of a tough one actually, but data collection, we will say that it belongs to the data engineering side of things. That's like harnessing of the data, and the data cleaning, I will allocate, maybe incorrectly, to the data scientists, but there's a large part of that data cleaning and data collection that you could say is an engineering perspective, or split them. Because if the data, again, is like, we're talking about automated data that's recorded from a device, then that data is clean. So like, we're looking for outliers and stuff, that's computationally cleaned. If we're looking at data cleaning from the perspective of like human input data, the cleaning process starts to be different. There are other biases and other things that we need to be aware of in the cleaning of data there. And then we move on, because I want to get to the last few slides. Virtual world, and I've put AI in brackets. So we had the real world examples, but we still got the data world examples. So the virtual world applications for each role, and then data science, you've got like the data models, KNN, SVM, and so forth. There's a whole bunch of data science models, and some of them are quite computationally intensive, which are the neural network type of things. They just need more processing power. We couldn't do neural networks without the processing power that we had. So in fact, I put them on the same line, not inadvertently, but yeah. And then, of course, the results that we get out of these. We didn't just build these models for the sake of building models and burning up our hard drive, our processors, making them do work for no reason. We're trying to get outputs or results out of these things in some way, whatever that might be, and we all have our different intentions. And then from the data engineering side of AI, it's a data acquisition. It's the same type of thing. And I could ask you a simple question. If I wrote the number 3, on a piece of paper, and put a CCTV array in it with an AI component to it, so like, could the computer tell me that number that I wrote, human, on a piece of paper, was the number 3? So that's kind of like acquisition of data. How have I got that in? Then it's a processing power for running, whatever neural network or whatever model that I decided I was going to implement on that question that we just asked. That's a processing power question. So you've got your data science and processing power, so like harnessed and working together. Because if the scientific part of it is the complexity of the model, we want to make it as simple as possible, and the processing power part of it, we want to be operating it, have the most processing power possible, so we can use this simple and fast thing to sort of like get our answer very, very quickly. And finally, the display of the output, which is the same thing. Once we've got our answer, whatever it is, we want our robot to talk back to us or do something useful based on all of the stuff that we did before. So we just go into acquisition and processing. Which category does data acquisition and data processing fall into? Data acquisition is data engineering. plus data science. So it falls into both categories, we're going to say. And likewise, data processing, like which category does that fall into? It falls into data science and data engineering as well. So here we've got a case where like actually some processes that take place in the system actually require both disciplines. So where we were showing that we had lots of segregation in different parts, in certain capacities, in other spaces, they're the same thing. And then I'm just going to fly quickly through the next few slides because I've got about 10 minutes left. History. We're just going to see how this evolves over time. But like if we look at data science, like back in the past, we might have been able to do like basic statistics, minimum, maximum, average. Even standard deviation was a challenge. Like 100 years ago, standard deviation was a big challenge because you had to find the mean square difference of the difference and divide it by the numbers. All of that without a computer, without a spreadsheet in front of you, that's a challenge to do. Then we move to more advanced techniques, as our processing power gets more. And you'll notice something on the data engineering side is just processing power, ultimately, and like delivery of content. And the more that we get, the more that the data science techniques can enhance themselves, so we can do bigger and better things. So all of a sudden, when we could do this minimum, average, standard deviation on like 100 things, when we started getting spreadsheets, we can now do 1,000 and 10,000 things. Then all of a sudden, we can start feeding them into systems and databases and using all types of programming languages to do like millions and millions of operations, and then do millions of operations per second as well. And finally, we move on to neural networks, which is sort of like the latest thing in all of the AI. Again, we couldn't do this kind of stuff 10 years ago, or you could, but with a supercomputer, but not with a regular computer. So this kind of stuff is just growing and growing, and we have Moore's law, which is the processing power doubles and the cost of computing halves, and that's advanced all of these types of techniques. It's not like we couldn't mathematically conceive them, it's more like we couldn't execute them, and now we're being able to execute more. And the more we can execute, the more we can ask. So it goes on from there. And I just stumbled upon this book actually when I was walking down the road earlier. It was written in 1941 as kind of like, and the author of this book had 124 illustrations, and he was very proud of that. He's written it on the front of his book. That's obviously quite a big thing. I mentioned at the beginning of the chat that I deleted 5,500 photos off of my WhatsApp chat without even knowing that was 1.6 gigs of data, and yet in 1941 this couldn't be done. So just a whole part of that. What do we expect in the near future? We expect the trend to continue. We're pushing against the same boundaries all the time. The more we succeed in each field, the more we're going to demand for the next field, and that's a data scientist and a data engineer effectively working symbiotically. They're not working, they're not two different things. Whilst we see for some parts they're two different things, in other parts they're not. They're working symbiotically in the system. And I said before, like the more processing power I have, the first thing I'm going to do is sort of like increase my data frame size and other things like that, and produce more computations because I can. So I will challenge the system in some way, and someone else in a different field will challenge it in a different way, but in exactly the same type of approach. And then we move on to our needs and demands. Data capture and data transfer, data processing, that gives us better data science, basically. From the data engineering enables data science, and data science demands from data engineering. So that's this enablement and demand thing. Maybe I could draw a line between the two and so that we can connect them. So both determine and guide each other. So whilst they're separate disciplines, they're also kind of like symbiotically the same, and there's some sort of overlap in them. And finally, progress is maximized when both components are working efficiently and symbiotically. So we can't have one without the other. And as our engineering techniques and processing power, data transfer and storage improve, that leads to our ability to execute better scientific models. So that improves too. And again, like if we just sort of like to take a massively global overview and look back in time, we've gone from paper we've actually gone from stones to paper to calculator, you know, and then to computers, and we don't even know what our next thing necessarily is going to be, but it might not be computers even. So like we're going beyond our realms in that case. And then we look at evolution. Where are we in the continual evolution? We're in a continual evolution of an arms race with ourselves to improve our capacities. So that's what we're effectively trying to do, and whoever does this best kind of like wins. And that's the achievement of both disciplines, the data scientist and the data engineer. And the immediate effects or benefits of this are clear and obvious. And the further future, we can now use AI to build AI. So the data scientist, I don't know, is it a data engineer or a data scientist? Robots to teach and build robots. So like this ChatGPT that's come out, like it's quite a recent thing. I've seen someone using ChatGPT to build their own ChatGPT. Is he going to build a better version of the same thing with data science? So maybe the data science and the data engineering roles will become one, although the components as we, so that when I say we, I mean the humans. So although we know them, they will remain different. So you've got different components, but you know, they're effectively the same thing. So, and finally, can you really separate them? And I put down here quite clearly in bold, in blue, yes, not only can we separate the roles, but we can quantify to what extent and who does what quite intricately. So I'm saying that, yes, you can definitely separate the roles. I'm telling you that. And then I move on to the next slide and say, can you separate them? And the answer is no, we cannot separate them. The two roles overlap, as the interface between them is too great to differentiate. So the answer is yes, and kind of like no. It depends where you are. We sort of like went through the whole thing, so it's sort of like nice to have an ambiguous answer to the whole thing, depending on where you sit in the infrastructure. And then finally, a question. You know, I can hand it back over now. But the question is was Pythagoras a philosopher or a mathematician? That's only because I stuck into Google. Was he a data scientist or a data analyst? And he was neither. But if philosophers and mathematicians were once confused as being the same thing, then you know, we have the same thing with data science. So, and at that point, I think I finish without having overrun on time and leave a few minutes for questions. So if anyone wants to ask. I presume the organizer arranges that.
Yes, we do. Thank you, Darren. Thank you for all your insights, and we sure are enlightened. And finally, we have the answer to this question: data science or data engineering. Now, having said that, guys, all of you who are attending the session on Zoom right now and also on LinkedIn and other platforms, if you have any question, feel free to go ahead and type it in the chat box, and I will go ahead and bring them forward. Darren, in the meanwhile, I do see some questions over there in the question and answer section.
Yeah, I just pulled them up. Yeah.
Yep. So can you just go ahead and start from there? Eric has a few, I see.
Yeah. Okay. Okay. Thanks very much, Eric. We know that data field is still new to business, hence this webinar, understanding the distinction between the two. So say a person is going for data scientist position, does that happen? Does it happen that businesses don't have data engineers and assume that data science is going to extract the data? The answer to that, the first question, is very much a yes. Like, and again, like this is going to go to like the small and large companies, but like do some companies expect the data scientists to do this type of data engineering role? And I worked for one company, it's on my CV, Red Hedge, you know, and again, it was a smaller company, so it wasn't a large company, it was like less than 10 people in size. And I was effectively like the data scientist for this company, but the reality was that I was the data engineer too. I was the person that was doing all components of that, because and initially it started as like you'll be effectively like the data scientist or someone who generates trade ideas, but very quickly it became like, you know, but we need a chart to see this, and we need to deliver, like, we need an output, we need conclusions, and we want to derive something from it. So it's kind of like you started with this core thing of scientific, and then so like moved out, and it became it's a huge engineering problem. And when I was talking about getting data into the system and so forth as well, it's that's not you, like the data scientist. Like if you haven't got an engineer giving you this clean, automated, nice data, that becomes your problem. So that's a good question. The answer is very much so, and it probably depends on the size of the business. Again, if how often and how to address this, it's just something like the reality is when you're working, you've got to get the job done. And so there's a certain, when I was working, at Mizuho, and it's got 200,000 employees, my role is much more segregated or specific, and I'm dealing with just purely trading, and I'm not. I don't care nearly about. I do care, but I don't care about the back office. Like operations are going on. That's someone else's responsibility. If something breaks down there, it's for someone else to answer to. And I'm just focused on doing my bit right. So it really depends and it goes down to the complexity and the size of the company. It's where you're working and what you need to get done in order for you to achieve the results that you deem to be successful. And it simply boils down to that. And does it happen the other way around? Yeah, again, it does. I mean, ultimately, the question might be you're always wanting this data science component, but and actually, so it does happen when I start and I'm embarking upon something, and especially again when it's like the smaller company type of thing, when I'm doing something myself, and I'm building like a crypto trading operation myself, and before I do any of the data science, I've got to make sure everything else is working. So actually, I want to be a data scientist, but I'm actually more of a data engineer to start with. I have to be. Am I going to use a database? Am I going to use CSV files? What am I going to do in it? And then will it scale up? Will I be able to build into something bigger? And then how much resources do I have as a person myself? So I hope that's answered your question in 3 different angles. So they're all connected, but ultimately, again, I think the bottom line of it is you're doing whatever you do, whether it's both of those roles or either one of them, or whatever proportion, you're doing it to achieve an output. And only you'll know that for each specific thing. I'll just read the next question. What are the main tech stacks and Python packages that each of the data science and data engineers work with? It doesn't just go down, by the way, to Python. So who is using more NumPy, Pandas, Skype, Matplotlib, Seaborn, SQL, Hadoop, example? When it comes to Python, it is kind of allocated. I don't know if it's fair or not as the data science language, but the data scientists tend to use NumPy, Pandas, and Skype, Matplotlib. They're all data science things. SQL, you're beginning to move into interfacing into the data engineering part. So that probably answers your question to a large bit. But again, where did NumPy come from in Pandas? They were the entire Python ecosystem was born on top of C++. And in order to be able to operate in Python, you kind of had to understand a bit of the infrastructure of data engineering, or why these things are there. Why do we even use NumPy? It's actually because it's fast and homogenized. It is the reason we use it. It behaves in a certain way. But the reality is a large part of the data science bit will be Python, but Python isn't restricted just to data science. It's a general purpose processing language. So it actually manifests itself all over, and it falls very much into the data engineering part in the sense that it lets you glue bits of the system together. And some people will call it a glue language. So it glues everything together. And that means that you can sort of pull things out of databases and pass them into your data science algos quite quickly. But on the other side of it, there's other languages that also do certain things. And when you're talking about web technologies, you're talking about JavaScript and Node. So they're different technologies. When you're talking about processing power or speed, and you want to go down to lower level languages or game playing. So I never even discussed that kind of thing. That'll be in a tech firm. You're talking about C++ and C#. So there's a whole variety of these things. I could only say that maybe data science lends itself, or its ecosystem is surrounded by, the data science bit falls around Python, or Python falls around the data science bit. But it's a very broad brush that I've answered that with. I hope I've answered those two questions. Is there any other question?
Thank you, Darren. Thank you for all your insights. And for all the participants watching our session on LinkedIn and YouTube, well, I have an eye on it. So if you have any questions, you can type in over there also. And for all the participants who are attending the session today, if you have any questions, feel free to go ahead and type it in the chat box.
We've had one more person type a yes, but that wasn't really a question.
Heba, do you have a question? Anything that you want to ask? Okay, so Heba wants to know, is data engineer an artificial intelligence engineer, or are these two things different?
It's a data engineer and an AI engineer. Again, like it's going to be semantics at a certain point because the engineering capacity. You know, a huge part of AI is what you might consider to be data scientists. But the AI, like a large part of the AI is going to need engineering. So that's presumably, or not presumably, but that's where you get an AI engineer. Again, because it's a symbiosis. You'll never have in any of these fields just kind of like data science on its own and no engineering. And you'll also never have data in like engineering. So like an AI engineer without any AI science. They have to kind of like live together because one effectively needs the other. So I hope that answers the question. I answer you know, the general original question with kind of like yes or no, and then this kind of question with a yes or no, because it depends on how you're segregating them, or where you sit in that stack from your personal viewpoint.
That is very well said. And as you already mentioned, it also depends on the kind of organization, how the KRAs are actually being defined over there also. So that's true. Any more question, guys? All right, Eric has one more question. He says, what is the best way to get into the first position in data science, data engineering? And last but not the least, what is the expected salary wise? Well, salary, Eric, I can tell you, it totally depends on the country, but I would, put Darren in charge to answer this question for you. First job in data science, data engineering.
Well, okay, what's the best way to get into like, okay, your first position? Work hard. Like, there's no shortcut, unfortunately. Work hard, go to university. When I was graduating, the tide had kind of like turned basically at that point in time already, and we're talking like 20 years ago. You already kind of like needed to have a like degree type qualification or a master's or that kind of level, and that's just become more and more the case. So that you know, whereas you know when I started it was like you know already maybe 50% or above the case. Now it's kind of like if you don't have that, you'll be at a huge disadvantage. You won't be considered because why? And the colloquial answer from like a recruiter or an HR person is, why would I recruit you when I could get someone you know who's more sophisticated? So it's just become if it interests you, first of all, because you need to be interested, it's then a case of just working hard at it. And one of the things actually, by the way, and I'll tell you all of this, I wasn't using Python 10 years ago. I don't think. I was using other languages, and the only reason I wrote a book, or like one part of the reason, I was using Python a lot towards the end, but someone said you can't write a book in Python. But the reality is like I can't tell you can't be a data scientist or a data engineer, like, and I can't tell you that you will be either. But what I can tell you is that if you work hard enough towards that cause, and that's what you want to do, that'll be pretty damn hard to stop you doing it if you are determined to get to that point. And that's just something about you. But the other part, like I might not be the best person to answer on salaries. It does really depend. Like I can tell you, like in the UK, salaries range between like starting types of things between 50,000 and 250,000. So it's not the best answer in the world, because that's a 5 times kind of like scale. But you're coming in at sort of like the lower end is £50,000 sterling, which is, I don't know, 60 or 70,000 dollars. And then a typical kind of thing. Then again, this is just in the UK; it's not around the rest of the world. It'll probably be 100 to 150,000 pounds sterling / dollars. So that's the kind of things that I generally see. And then
that is very well said. And Eric, just to add to that for you, we have students coming in from more than 60 countries. So there's one thing I can absolutely tell you is that the average salary of a data scientist is almost in all the countries more than the average salary that the people get, So that's one thing for that matter that you should know. In the United States, it's close to 85,000 thousand dollars, and the average salary in the United States is around 50-55. So it's,
and actually, I'll add something
to
that, which is, because I'm surprised to hear that, but I'm surprised and not surprised. But actually, 20 years ago, when I was looking for a role, it was finance that dominated, and the average salary in finance. I actually moved out of engineering into finance because finance just paid multiples, and we see the roles beginning to reverse over time, and that trend will continue, because the data scientists and data engineers are just perceived to be much more important now. The contribution is just much more.
That is true. And speaking of which, 27% of jobs in data science is actually in the finance industry, and that's where the money actually is. So it's more or less a marriage between the two industries, as I can say. And yes, Eric, so in order to get your first position, we have a lot of courses that we also offer. Darren also teaches with us in one of our university's programs. So I'm pretty sure we can be of help to you in this case. Heba has one more question. I see. Is it must for data scientists to be stuck to his background field, or it depends on his practice and future experience? Now, Darren, we get this question a lot. Okay, let me make it more generic. Let's say if somebody comes in from a finance industry. Let's say he has worked in finance for, let's say, 5 years. When he or she learns data science, is it necessary that they should stuck to the finance industry itself, or how hard it is to change transitions? Because domain expertise does matter, as far I know,
It does and it doesn't. If you're driven, you won't be stopped. But I actually had the reverse. I came out of engineering and went into finance, and people tend to pigeonhole you, and don't let that ever stop you. So they tend to say you can't do this. And I've seen plenty of examples where people have been told they can't do something, and they worked hard enough at it that they did it. Not only did they do it, but they achieved much better. And when I came out of engineering and walked into finance, everyone said you will never trade, and you'll never be a trader, and you'll never make £1 million, and this guy will be better than you. And all of those things turned out to be incorrect, and not just were they incorrect, but they were incorrect by orders of magnitude. And then again, like after I'd been a trader for many years, like people told me you can't be a data scientist. Like, how are you moving into there? You haven't got the skill set. But again, that couldn't be further from the truth. My last 2 or 3 roles have been pure quant trading and data science type of roles. And just recently, of course, with you guys, I've started teaching Python, and I didn't think that all came about because I just kind of like picked up the language and kind of like specialized in it more, and did a bit more, and then sort of like found myself going up the ratings on sort of like Stack Overflow, answering people's questions. And then I thought, oh, maybe I'll just kind of like write a book and see how that goes. And you feel like it went better than expected, maybe, or something. And like, so you will be pigeonholed, and there are things that kind of like stumble, but like you're walking along a path, and if one kind of like tree that's fallen over kind of like has blocked your path, you won't get there. You're going to climb this mountain, and if you decide that the mountain was too big before you left your room, you'll always just sit in your chair and never have left the room. Whereas you might agree that at least attempting to go on that journey and dying halfway up the mountain might be better than never having attempted that journey. so again, hard work, and that won't stop you. Like that's just a myth. Some people will actually argue that coming from another background is a benefit rather than because you have another perspective. And so someone telling you that you can't do it or it's a headwind, you may well argue back, well, I've got other skills that you don't now possess, and that's a synergy. And I've even actually seen a lawyer coding, and like, he was actually amazing. I couldn't nearly believe it, because I was like, I'm the specialist here, not you. You know, on the trading desk, and you know, he just starts coding like it's nothing. And I'm like, how did you even learn that? He just I still like picked it up and tried. So I hope I've answered that one as well, as best I can.
Well, I think yes. If anybody has any follow-up question, feel free to go ahead and ask. I see Eric typing in. Coincidentally, I'm currently in finance in London. So Eric is probably from where you are also, Darren, and he is really enjoying the session. Thank you, Eric.
Okay. Where do you work for, Eric? Like, or who do you work for? I spent my entire, like, maybe we'll come and say hi one day.
Well, he sure can. Anybody else has any more question, guys? Anybody? We'll wait for another 5 to 10 seconds. If we do not see any more questions coming up, we are going to go ahead and wrap up the session. In the meanwhile, while we are waiting for the questions, I would like to thank all of you for participating in this session. I hope you learned something new, and we are looking forward to seeing all of you into the program also. We have multiple programs to offer, both certification and degree programs in data science, and we would love to be a part of your journey professionally. Any more question, guys? Well, I don't see any more coming up, Darren. So I guess it's goodbye then. Thank you once again. Thank you, Darren, for your time. Any last words for the participants, Darren?
No, it's just kind of like, I've actually, whilst I was constructing this, because I never thought of these things, I actually learned a lot. And you have to make sure to an extent that you can deliver it properly, and that it's coherent, and putting that coherence together, it opened my eyes up to a tiny bit extra. So it was a learning process for me as well. So I'm glad that I did it, and I'm glad that, I hope that everyone's taken something out of this too.
Perfect, Darren. And as we have discussed and said many times, learning is a two-way process, and that's how it works. So thank you once again, Darren. Thank you for your time. Thank you all our participants who tuned in, took out time from their busy schedule, and I wish you all the best for your future, and have a good day and stay safe. Thank you, everybody. Have a nice day. Bye-bye and take care.
Bye.